Today we're going to start section 6.3. Section 6.2 is the addition and subtraction of rational numbers, and now we're going to move into multiplication and division of rational numbers. Computationally, multiplication and division are easier processes for fractions than addition and subtraction are. They're a bit more challenging maybe to visualize. Addition with visualization works really nicely. You're just sort of adding pieces of the pizza, filled in pizza, kind of thing, or taking them away. But multiplication, it's a little bit trickier for a visual, but we'll do it. The multiplication of rational numbers works like this. If you have a over b and c over d and they're rational numbers that you multiply, then a over b times c over d is a times c over b times d. So we're just multiplying across the top, multiplying across the bottom. What this does is it says that it doesn't matter whether your denominators are the same or not. It's completely irrelevant. And that's why it's easier, is because I don't need common denominators when I multiply and divide. It's only an addition subtraction thing. Now let me show you how we do think about the visualization for what's happening here. So I'd like for you to draw a rectangle. There's nothing special about the rectangle anyway, it's just easy to draw for the purposes of our discussion. We could similarly draw a circle if you wanted to, it wouldn't hurt anything. So what I'd like to do is I'd like for us to do 3/5 in this rectangle. So yours might actually look a little more even than mine does, but we'll see. I need to split, and I'm going to do it from the top down. So I'm going to do vertical bars to split 3/5. So 1, 2, 3, and 4, 5. Okay, it's quasi-believable. I've split it into 5 vertical bars, and I'm supposed to be representing 3/5 of my shaded diagram. I'm going to shade the diagram, so I'm going to shade in 3 of those 5 bars, okay? So shade in 3 of your bars. Actually, let me change it to a thicker one. Okay. So we're just going to create the diagram first, and then we're going to talk about how you can sort of think about it. So if you want to jot yourself down a reminder for the thought process, you can do that. The next thing we're going to do is we're going to make a diagram for 3/4. But instead of dividing it, again, vertically, which would look really confusing because I've already got division bars, we're going to divide it horizontally. So I'm going to make 4 horizontal bars, okay? So to do things with from 4 is actually really nice. So you can just split it in halves and then halves again. That's less believable than my vertical bars, but that's okay. And then we're going to shade in our vertical bars, but we're only going to shade in the blue portion that we have. So ignore the rest of the part that's not shaded. It's just not going to get shaded. Just ignore it for a moment. Okay, I'll explain in a sec. We're just going to shade in the vertical bars for the blue part. I changed colors just so you know. So here's 1 bar, 2 bars, and 3 bars. We'll justify how this gives us the answer, and then I'll talk about why the description will make sense. The red part that I shaded that overlaps the blue, how many boxes did I shade in? 9. How many boxes does the original diagram have? Or you could talk about what size is each box. There's 20 boxes. Each box has size 1/20. So this is 9 out of 20. In terms of the values, you can see 3 times 3 is 9, and 5 times 4 is 20. Okay, so all the numbers match up. Now let's give some context to what's happening here so you can see the idea. So imagine the original box is a cake. Okay? 3/5 of the cake is left over after you took it to Super Bowl Sunday. Yeah, 3/5. That's the blue part. Okay? So 3/5 is what's left over. Of the 3/5 that's left over, namely only the blue part, somebody eats 3/4 of it. Or you could say 3/4 of it's left after somebody eats something else. I don't care. It doesn't matter. But that 3/4 part that's shaded, the reason that we only shade the blue part is because that's the only part that still exists, right? It's the only portion of the diagram that we're actually considering because it's the only portion that we have left over, or whatever, however your context is. Does that make sense? So in some sense, what you're really saying even is I didn't really need to divide these boxes over here. I mean, I don't really. They sort of weren't there anyway. The cake, if I split it up or whatever into these pieces and so forth, didn't really include that. But having those bars there makes it easier to talk about how big each of my boxes is, because I can count all the little boxes in the diagram if I draw them in that way. You can see that each box is a size 1/20th of the original whole cake. All right. Let's talk about some properties that exist for rational numbers. Theorem 610 talks about 610 talks about the identity and inverses. So the multiplicative identity is exactly the same as what happens when we have integers. The multiplicative identity is the number 1. Okay, it's the number that we multiply something by, and it doesn't change our value. So we multiply a over b by 1. You can multiply it on the left. You can multiply it on the right. Either one works because multiplication is commutative, and I am left with the same number, a over b. The multiplicative inverse is the value that I multiply by to get back to the number 1. So as long as I don't have the number 0, because I can't multiply 0 by anything and get 1. As long as I don't have the number 0, it will have a multiplicative inverse. For example, if I had the number 5, what would I multiply 5 by to get 1? Well, 1 over 5. So 1 over 5 is the multiplicative inverse of the number 5. And if it feels weird to write it that way, remember again, 5 is the same as 5 over 1. And we get multiplicative inverses by inverting our fractions, reciprocal of our fractions. So that's where that's coming from. Theorem 611 is the distribution property of multiplication over addition. It happens to work over subtraction as well. It says that if I have rational numbers a over b, c over d, and e over f, and I multiply a over b times the addition of c over d plus e over f, then I'm going to simply distribute a over b through to each of my individual fractions. So the a over b gets multiplied by c over d, and the a over b gets multiplied by the e over f. Okay, so it's the same distribution property that we had for integers and whole numbers as well. Works the same way. Our next one is a property of equality. Now, we had an addition property of equality. You'll remember the visual that I described is how if two people that were the same height were standing, and then they each put on 3-inch heels, they increased their height by 3 inches, they'd still be the same height, right? You add something to each of their heights, the heights remain steady or constant. The same is true for multiplication. If you multiply, so imagine taking something where you were enlarging it, so you enlarge things on your phone all the time. Anybody zoom in, zoom out all the time? Yeah, me too. I'm constantly doing it on my iPad. So if you use the same zoom percentage, that's the same idea. That's the idea of a multiplication percentage. So if you were to multiply a over b and c over d, which are equal to start with, by e over f, then their results, their products, would also be equal. Inequalities actually also work, but there's one caveat to that. So if you have a over b and it's greater than c over d, and you multiply it by a positive number, then that relationship still holds. The first value is still greater than the second. But if you multiply a over b and c over d by a negative number, the direction of the inequality changes. So you see here, this one was positive, you're multiplying by a positive, the direction stays the same. I didn't mean the positive. It's greater than. That's what I meant to say. Greater than, you're multiplying by a positive. The direction stays the same. This one's greater than, but you're multiplying by a negative. The direction of the inequality changes. And I'm going to do an example for you of this. So let's say you had 5 halves and it's greater than 1 half. And you would agree, right? Sure, no problem. And just for the sake of making it easy, we're just going to multiply by -1. -1 can be written as -1/1, so it works. If I multiply these both by negatives, I now have -5 halves and I have -1 half. Which of those is smaller? The -5 halves is smaller now, right? It was bigger originally when it was positive, but now it's smaller. And so the direction of the inequality changed. Right? So if you multiply by negatives, inequalities change directions. Yeah, I think it's our last property. Our last property in this section is the multiplication property of 0. 0 is wonderful because when you multiply it by anything, you get 0. That's all it says. And again, this happened back in whole numbers. It happens in integers. It also works for rational numbers. 0 multiplied by anything is 0. Now, like we did in section 2, when we are solving equations, we're using a lot of these properties, sometimes without even sort of being cognizant of the fact that we're doing it. We're just so familiar with the idea that it just makes sense. I can do this. So the questions that are going to follow the next couple examples are going to have us solve something and identify what properties that we're using as we use them to the best of our ability to sort of actually really think through what's happening here. So this one actually says 3/4 x equals 1/5. Now there's more than one way to do the problem, but I'd like for you to think about the idea that we want to move the 3/4, and we'll just keep 3/4 altogether as we move it. I recognize we could multiply by 4 and then divide by 3. That's another possibility. But we're just going to keep the 3/4 together. So if I wanted to move the 3/4, what would I do to get it to go to the other side or to eliminate it, to shift it over? Multiply it by its reciprocal is one way to think about it, and it's a really good way to think about it from the ideas we've sort of been exploring already. So this reciprocal is the multiplicative inverse, right? So that's why we chose that number, is because it's the inverse. Our ability to multiply on both sides is the multiplication property of equality. So that's what allows us to do it. Okay, so there's the choosing of the value, and then there's the actual using of the multiplication. So there's 2 properties that are play in that. Now, when I multiply the 4/3 times the 3/4, and I end up getting a 1x, that's the multiplication, or multiplicative inverse happening again, because that's what it said. Multiplicative inverse is when you multiply by the reciprocal, you get the number 1. Over here, we have 4/15. So again, we use the property of the multiplicative inverse. Okay, so this is the same 2 steps. And here we're also having the definition of multiplication. Right? That's why the 4/15 came about from 1/5 times 4/3. I know you feel like you're done. You actually aren't quite done yet. The reality is 1 times x is equal to x. Agreed? That's one of those ones we definitely take for granted all the time. Once it's there, we just ignore the fact that there's a 1. When it's not there, we include the 1 back when we want it. Okay, so we drop it and we add it in willy-nilly a little bit. What we're doing is we're actually using the multiplicative identity when we do that. Because the multiplicative identity says when I multiply by 1, I don't change the number. Hence, when I multiplied 1 times x, I didn't change the number x, it's just x. So it's a fairly simple problem, and there's actually quite a few properties that we used in the midst of it, isn't there? The next one's more complicated because of what? The addition part. The addition part means that I also have more pieces that are going to be combining. I also noticed that with addition, that means, the addition especially, it means that I've got to find common denominators to make things work. All that is going on. I don't know. What do you guys want to do? Do you want to find common denominators first? Do you want to combine fractions on the left side and the right side? There's lots of things we could do in lots of order. So somebody give me a starting point. Common denominators. Okay. If I'm going to get common denominators, I might as well get common denominators for every fraction. You agree? Awesome. So we're going to do that. I have 3, 4, 6, and 2. 12 would be a common denominator for that. So if I use the common denominator of 12, then the first one would be multiplied by 4. The second one would be multiplied by 3. The third one by 2. And the last one by 6. Okay, everybody good so far? Okay. And I think it's reasonable that we could just write that we're getting common denominators over here. It's part of the process of adding fractions. All right, so let's adjust each of them. I now have 8x over 12 plus 3 over 12 equals 2x over 12 minus 6 over 12. Again, several different things I could do next. One thing you might want to do is to go ahead and make single fractions on the left hand and the right hand side because the denominators match, right? So we could go ahead and say, okay, well this is 8x plus 3 over 12 equals 2x minus 6 over 12. And what we really did to do that is that we got addition, or we used addition of fractions or rational numbers. It's not a hashtag, it's a number sign. Okay, so I'm going to direct us to the next step because it's going to simplify a whole lot of things right at once. We're going to multiply both sides by 12. Again, not the only way to do the problem, but it's a really nice way at this point. Why 12? Because the denominators, say it again? The denominators are the same. Mm-hmm. And the reciprocal of 12 is the 1/12, namely the 12 that's in the denominator, right? So what I'm actually using when I multiply by 12, I'll actually write it in red to correspond to the red that I just used, is the multiplicative inverse. I think I just said identity a minute ago. I'm sorry. Inverse is what I meant. So like Emma pointed out, the whole idea, the reason it's nice is because the 12 in the denominator cancels with each of those 12s. And lo and behold, I'm actually left with no denominators, and that's very friendly. So the last pieces that we're going to do actually fall back in the realm of whole numbers, but they still work for rational numbers. That's great. So we're going to subtract a 3 to move it to the right. That gives me 8x equals 2x minus 9. That is a additive inverse. Hang on. Inverse. And identity. So why do I say it's identity? Well, 3 plus 3 is 0, and you didn't see me write a 0 down. I just didn't write it. That's the additive identity. When I add 0 to something, it doesn't change it, so I don't need to write the 0 down. We also then can do the same thing with my x's, so I can subtract the 2x. So now I have 6x equals negative 9. So again, that's the additive inverse and identity. Again, identity because the negative 2x minus the 2x right here actually gives me a 0 that I didn't write down. I rather ignored it. And then what's the last thing I would actually do? I would divide by 6. I'm going to write it a little bit differently just because of what we've already done in this section before this. I'm going to write it as though we're multiplying. Any idea what we would be multiplying by that would be the equivalent? Yeah, 1/6. So not because there's anything wrong with divide by 6. You can certainly write that down. But just because it's easier to identify the property, I'm going to write it as multiplication by 1/6. And again, the property that we're using on that is the multiplicative inverse property. And if I do that, again, I'll write it in this time just because we're using this new property in this section. I get 1x on the on the left. And I get -9/6 on the right. So that's the multiplicative identity. When I change that to just say x, I'm out of space. Let me do this. So I end up with x equals, and it was negative, right? -9/6, that's the eliminating of the 1 in front. And then I need to reduce the 9 and the 6 by dividing both of them by what? 3. So that's simplification or reducing. And I end up with x equal to -3/2. Crazy stuff, right? It's a lot of steps, but when you start writing down all the steps of things, why justification for why you're doing things, it gets really messy very quickly. All right, we're going to shift gears then, and we're going to take a look now at division. The division of rational numbers says the following: if a over b and c over d are rational numbers, and we divide them, a over b divided by c over d, that will equal e over f if and only if e over f is the unique rational number such that a over b equals c over d times e over f. And let me show you numbers, sort of justifying that so you can see why it works. I'm going to do it with whole numbers just because the image of it is a little bit easier to see why. 6 divided by 2, what does that equal? 3. Okay, so I'm sure at some point along the way, whether it was with somebody talking to you or you talking to another child or maybe a friend along the way, you had to sort of think through why 6 divided by 2 is equal to 3. So I have one of my 6th graders that still kind of struggles with her multiplication and division facts. We work on it a lot. And so I find myself asking her a lot, not necessarily with these specific numbers, right? When I want to know what 6 divided by 2 is, I ask her something like this. I say, what times 2 is equal to 6? Right? Because the reason we spend so much time, and the reason I tell my child specifically that it's so important that they know their multiplication facts, is because it makes division easier. Because if you already know one piece of it, you can turn the question around into the piece you already know once you're talking about division. So the reason that 3 is the answer is because this 2, when moved to the other side, just like it's showing you this c over d moved to the, well, I shouldn't say to the other side. They've got it flipped from that, but grouped with the answer anyway, right? Ends up giving me the 6 I started with, the original value. So what would I multiply 2 by, or 6, 2 by to get 6? All right, cool. So that's what it is. There is an algorithm for division, and I know you guys have seen this used before, and there's different mnemonic sort of reminders for thinking about it. Let me just identify this with you, and then I'll actually show you the real reason why it works, not just the mnemonic device for remembering that it does. Algorithm for division of fractions: if a over b and c over d are divided. So you've got a over b divided by c over d. Nothing can be 0. It doesn't work with zeros, okay? So a over b divided by c over d. It's the same thing as a over b times the reciprocal d over c. So instead of dividing, we flip and multiply. I've seen my student teachers describe it like that when they've done middle school student teaching with my observations before. So we flip and we multiply. And again, that's one of those things that's very handy to do. We can certainly do it, and you can be really, really good at doing it and still not really have any reasoning about why in the world should that be true. Where did that come from? So I'd like to show you where it came from because it's really not that mysterious and it's very clever and easy to justify, to be honest. So let me show you what happens if we write it down longhand. So I'm going to do A over B divided by C over D. And instead of writing the division as the bar with the dots on the top and bottom, I'm going to rewrite it in a bigger fractional form. So I have A over B divided by C over D like this. Right? That's one of the ways we talk about division. Right? We can turn a division symbol into a division bar as a fraction. All right, well, this is actually called a complex fraction when you have a fraction inside of a fraction. And the way we eliminate that happening anytime we deal with complex fractions, whether they're numbers or variables later in like an algebra or an algebra 2 course, is that we get them all into one fraction on bottom, which this already is, it's C over D. And we say, okay, well, I don't really want the C over D. I'm going to multiply by the reciprocal because when I multiply C over D times D over C, I get 1. So I know I'm not quite finished with this step, but the reason I did that is because I want a 1 down here. Okay, that's why I chose that. But anytime I deal with fractions, anything I do to the denominator, I have to do to the numerator. So if I multiply by D over C in the denominator, I need to also multiply by D over C in the numerator. And we can see that what we end up having is A over B times that D over C. And the multiplicative identity, in this case it's a division identity as well, because multiplying and dividing by 1 are the equivalent, leads me to having simply A over B times D over C. Which is exactly where we're headed. Yes, Emma?
Can we write it like AD over BC, or do you want us to
no, you can definitely write it that way. I was just mirroring it back to what was looking like this. But you bet, you can definitely write this, and in fact, most of the time I'm sure you will, and I will too, like that,
Okay.
for sure. Crazy, right? It's really not that challenging. It's really not that hard to show, but it feels like magic if you don't actually spell it out. All right, I would like to show you one more thing. This will end our sort of discussion of specifically division, and then we'll jump back in next time with definition of exponent. I want to talk to you about what it actually means to divide by a fraction, because I think that feels funny sometimes. What does it mean to divide by 3/4? What does it mean to divide by 4/7 or whatever? What does that mean? I mean, like, we flip and multiply and we can do the operation, but what does it mean in context? And so I'm going to give you a description based on whole numbers, and then we'll switch it into fractions so that you can see that the description still works. So there's two ways to describe 6 divided by 2. One way is you can say, actually let me say it without writing it down. One way you could say, I'm going to take 6, right? And I'm going to divide it into 2 groups. I got 6 people, divide them into 2 groups. Well, that doesn't really work all that well when you go to 1/2. 6 people and divide them into half of a group? Like, that sort of sounds funny. It doesn't really make a lot of context sense, right? So the other way that we can do that is we can describe it and we can say we're going to break the 6 or divide the 6 into groups of size 2. So instead of 2 groups of size 3, I end up with 3 groups of size 2. And we can draw that image, and we can imagine doing cookies. So does anybody get to go to McAllister's or like City Bites and get their cookies? They're huge. They're the kind of cookies you split between someone usually, unless you're, really hankering for something sweet, because they're big. So imagine doing that. We're going to take our cookies, and I'm going to draw 6 of them. Because I have 6 cookies, and instead of making 2 groups of 3, I'm going to group them into groups of 2. So here's a group of 2, here's a group of 2, here's a group of 2. And the answer to 6 divided by 2 with this image, of course, is that there are 3 groups. This structure of language fits better for division into 1/2. And the other one works, I'll say it in a second, but this one works better. So we would have, again, that same 6 cookies. Oh, I want my 6 cookies. I don't want to have to draw them again. But instead of having groups of size 2, we're going to have groups that are size 1/2. What does that mean? Well, I'm trying to find out how many halves are there if I have halves of cookies instead. Right? So if I split each of my cookies into a half, so again, the language is that I'm going to break 6 into groups of 1/2. How many halves do you end up having? There's 12 now, right? So 6 divided by 1/2. How many halves are there in 6? Is that answer 12? Now let's just, for just a second, step back. The other way that I told you over here is that I could say 6 divided by 2 means I split it in half, right? 2 groups of 3. You could say I have 6 and I have groups, and if my group is half of a group, my 6 people is half of a group, how many people's in a whole group? You could do that. I'm still going to get 12, right? If 6 is half the members of the group, then the whole group is 12 members. But I think the visual works better when we ask ourselves how many halves are there in the number 6. All right, so we'll stop there today. We will pick up on definition of exponent next class period.